Today I would like to talk about the subject of conic sections. Conic sections. I rather expect that you are familiar with the subject to some extent. Yet I shall try to make a completely fresh start on the subject, conic sections. So just as the name suggests, a conic section is a curve which you obtain by taking a cone and letting it be intersected by a plane. This is a subject which is pretty ancient, okay, so a rather old subject and very well developed subject. And when I talk about a cone, of course, it's not the prep school cone, okay, with an apex and a base, so on and so forth. No, you should imagine a circle. So I will be talking about the right circular cone, yet exactly what it is. Imagine a circle, and then erect a perpendicular at the center of the circle to the plane that contains the circle, okay? Take a point on that line. Let it be called the axis. Let's take a point on the line, on the axis, and join that point. Let that point be called the apex. Let's join that point to a point on the circle, and let the point on the circle move on the circle. So the straight line joining the apex to the point will simply describe a surface which is just a surface, except it will have one, so to speak, bad singular point, the apex, where all these straight lines intersect. The straight lines in question are called the generators of the cone. Right, so what happens if you intersect a cone with a plane? Let me approach, now that the picture, it's a three-dimensional problem, and it's not everybody's cup of tea, but then again, and it's also difficult to put it on blackboard, but I shall attempt it all the same. So let this be your cone. So let's start looking at the cone sideways, okay? So from the side we are looking at it, and what you see, of course, is when you look at it from one side, you look at it sideways. What you see is, of course, okay. So let this be the axis, okay. And of course, what you do see is, well, this is okay. I have to be careful about it. I have to get this thing right, otherwise, really, it makes no sense. Okay, so let this be the axis. And if you look at it sideways, you see the apex here, and then essentially what you see is a pair of straight lines. Okay. Okay. So if you look at the cone, from the side, this is what you see essentially. Okay. And let us once again assume that the cone, which we are seeing now sideways, is intersected by a plane. Well, let's say something rather like this. Okay, so what we essentially see, so let this plane be called pi. Okay, so what we have got essentially is a triangle here. Okay, right now. I will now ask you to, okay, so, well, for future reference, let us consider the circle, the in circle of this triangle, okay? So, you know, it's a thing that's very difficult to get right, okay? So, drawing the triangle first and the circle next, that's foolish. but we had to do it now. Okay, so you've got this in circle, and you've got also the x circle. That's even more difficult to get right, but I shall try to get it right. Well, it's something more or less like this. Okay. Right. So that's essentially the configuration. That's essentially the configuration. If you look at it sideways, well, what the circles mean, they will become clear in a minute. Okay. Now, forget the circles for the moment. Forget the circles. Let's take this situation. In fact, forget not only the circles, forget this plane seen sideways. So let's just imagine this axis and these two straight lines, okay? And let us rotate the whole thing about the axis, okay? So that this pair of straight lines will generate a cone, okay? And I want you to imagine it as not as your prep school cone, but as a surface which is extended infinitely in both directions, right? So I'm turning this into a three-dimensional configuration. Okay, that will not be easy. So I will have to appeal to your imagination. So this circle turns into a sphere like this. Okay, and of course these points of contact will be transformed into a circle. Okay, so please imagine that you've got this cone and you've got this sphere which fits into it and touches the cone along this circle. Very good. And very much the same thing happens here. Okay, so that you've got this circle along which this, so to speak, circle of tangency, along which the sphere touches the cone, actually. So these things are difficult to get right. I will be correcting and recorrecting my picture until it looks anything like real. Okay, so that's what we have. Right. So I want you to, okay, so the plane now I want you to imagine, so let's sort of not look at it quite sideways, but sort of try to move a little bit upwards and try to look at it a little bit from above. So the picture that you have got is this plane. Okay, this plane, which we have called pi. Now it's as I say, it's a picture that's difficult to get right. It's difficult to get right. I shall do my best. I shall do my best. That's this sphere. Okay, so there we are. Right. So you've got this plane. That plane, okay, that plane intersects our cone in some kind of curve. So let me use a little bit of color in depicting that curve. That curve is going to be something roughly like this. And I want you to imagine this curve, okay, this roundish curve, also as indicating the plane that intersects this thing. So if you like, and that of course this plane will touch the small circle in a point, okay, which is below the, it's on the other side of the sphere, okay, and it will touch this sphere, okay. So let's start giving names. So let's call this sphere sigma. Let's call this sphere sigma prime. Okay, let's call the plane pi. Okay, and and there is this point in which the plane touches. Okay, so there are 2 points in which, and in one of which the plane pi touches the big sphere, the sphere sigma. So please imagine this plane going like this. Okay, now as you can see, it's a difficult picture to draw, and it's not all that easy to imagine. Okay, so let's call this point the point in which the plane pi intersects this, touches the sphere sigma. Let's call it F. And let's call the point in which the plane pi touches sigma prime. Let's call it F prime. Okay. Right, so that is more or less the situation. That's more or less the situation. Now I would like to draw your attention to something interesting. Now let's take any point, an arbitrary point. Okay, so we would like to understand the nature of this red curve. Okay, so what's the crucial, what's the defining, what's the characterizing geometric property of this curve? Well, I hope in a minute we shall get hold of that. Okay, so here it is. Let's take a point on this curve, call it x. Okay, now, okay, so let's call this apex omega, if you like. I like it rather that way. Now, I want you to imagine the following. Join omega to the point x on our curve and extend it. And, and let omega x intersect, be tangent to the sphere, large sphere sigma, at the point P, let's say. And of course, this point P depends upon x. So let's call it, if you like, P sub x. So as x changes, this P will change on the on this circle of tangency. Good. And in exactly the same way, I can also look at the point, okay, corresponding point x prime on the small circle. I'm sorry, P prime, I meant P prime. And of course, you should notice that this P prime is also dependent upon the choice of x. So as you change your x on the red curve, P and P prime will change their positions on the respective circles of tangency. Well, that's great. Now, still, we have not seen exactly what characterizes this red curve. What's so special about this red curve? What's the crucial property of this red curve? Well, you can do it as follows. So now I want you to think separately and imagine with me a sphere. Okay, so let this be a sphere. Okay, so let's do it like this. Let's take a circle if you wish, and let's take a point outside. So let's call that point x. You've got a circle. You've got a point outside it, so you can draw two tangents externally, like this. It is, of course, a very elementary fact. It's a very elementary fact that the lengths of the line segments joining the point x to the points of tangency, that's to say xa and xp, they are the same. They have the same length. Well, they are congruent. Well, that's very easy to establish because you see, well, let this be center be O. XAO is a right triangle, XBO is a right triangle, and they are in fact congruent. So that's very easily established that the length of XA is the same as XB. Now, I want you to imagine the following. What happens if you rotate this whole picture about the straight line joining X and O? Well, if you do that, then what you are going to get is that the points A and B, so this circle will become a sphere. Can you imagine that? The circle will become a sphere. And the point A and the point B will be part of a circle like this. and the straight line segments joining the point X to not only A, but to any point on the sphere, okay, they will all have the same length. They will all be congruent. Okay? So, let me use a little bit of color to illustrate this thing. So, so that's the thing. And finally, of course, let me should create a Z element as created. So let's work this sphere a little bit so that it looks like a real picture. Okay, so here is your sphere. Okay, that's excellent. So if you take a sphere, and if you take a point outside it, then there are infinitely many tangent line segments joining the point and the sphere. Okay, and these line segments, they all have the same length. They all have the same length. Now, let's get back to this picture. This point X, I want you to imagine, so you've got this sphere sigma, the point X is somewhere outside. And if you draw one tangent to it, you get XP. And the other tangent is XF. So this tells me that, in fact, of course, this is a three-dimensional picture. So this length XF and the length XP are the same. Okay, so please notice that the length XF is the same as XP. Now, okay, so perhaps I should let me write this in this form, or perhaps let me indicate this in green. Okay, so XP and XF, they're the same in length. Now, in exactly the same fashion, if you take the length XF prime, I don't know if you can really visualize this thing, even with the help of the picture on the blackboard. This F prime is at the bottom, so this is your sphere, sigma prime. F prime is sitting somewhere here, okay? And you are drawing a tangent line from X to F prime. And so that tangent line is only partially visible to us, okay? So that's F prime. And then there is another tangent line, drawn tangent line segment from X to the sphere sigma prime, and that's exactly the line segment that joins X to P prime. Okay? So that means this length, the length XF prime, let me indicate it in double dash, and the length XP prime, they are the same. So in exactly the same fashion, I've obtained XF prime equals XP prime. Right. Well, here we have got something crucial at least. So that's the point X. So it means that if you add XF and XF prime, you get the sum of, so the sum of the line segments XF prime is the same as XP prime. So therefore, so notice that if you add XF and XF prime, that's equal to XP plus XP prime. But so of course this P depends upon the choice of X, obvious. P prime, well, it does depend on the choice of X as well. Yet, so the result, so XP plus XP prime, that is in fact PP prime, the length. Well, although P and P prime, they depend on X, I want you to imagine, çocuklar. So bakın, so let's imagine you've got, okay, so how was that? So you've got this cone, you've got this circle perpendicular to the axis, you've got another circle perpendicular to the axis, and you are looking at lines through the apex and the line segment that lies between these two circles. So that's this thing. Okay, so that's your P, that's your P prime. Okay, so you can move P along the cone. Okay, so you can, for instance, make another choice like this. Perhaps I should let me use blue. So let's make another choice like this. Okay, so let's say Q prime. Well, the length P prime and Q prime, they are the same. They are the same. So you can choose it anywhere you like, anywhere you like. Okay, so you can take another one like this and that. Let's say this is R and R prime. Okay, so they are all the same. They are all the same. So what does it mean? It means that although the point P and P prime, they depend on the choice of x, as x moves along the curve, the length of the line segment PP prime is independent of the position of x. So this is a constant. So you've got xf, so this is a constant. Okay, so this thing, so it is, so it's a well. So this has characterized the curve, this red curve, with the following rather nice geometric property, that it's the kind of curve, so this red curve, the curve that I have obtained by intersecting a cone by means of a plane, is a kind of curve which has in its plane, in the plane that contains it, two significant points, f and f prime, so that the curve is characterized by the following property. The sum of the distance of any point on the curve to f and f prime, the sum is a constant. That characterizes a curve. So this gives me what I like to call the first characterization, of conic sections. The first characterization. It is okay. So it is. So if you intersect the cone with a plane in such a way that these spheres are on the same side of the apex, the curve, which is going to be a roundish curve, is called an ellipse. The first characterization is as follows: an ellipse. Okay, so observe that I've got a blank here, so I've got an alternative curve to think about. An ellipse of, well, here is a word that requires explanation. Çocuklar, the word is focus. And if you are an ignorant or well, not ignorant but callous person, you can always say, of course, far. Okay, so this is one focus. You can always say two focuses, but that will be a scandal, among intellectuals. You never say focuses. The plural for it is, I have never learned the correct pronunciation. It's either foci or foci. Okay, two foci. Like one focus, two foci or foci, I don't know. Okay, so an ellipse of foci, f prime, and well, so that's foci is the plural of focus. Okay, so that's one piece of terminology that's going to be important, and And another piece of terminology, here's the thing, major diameter. I'm sorry about, and why is it major and why is it diameter? That will have to be clarified later, but just take this as a piece of terminology. So there are two things defining an ellipse. One is your pair of foci, and the major. So this is a pair of points, and you've got a major diameter, which is a length. It is traditionally denoted 2a. It's a length. Okay, 2a is the set. Okay, here's the thing. I'm writing it in set theoretical notation. So those points x in the plane, those points in this plane, and you can imagine this as, you know, there's a Cartesian plane, okay, R2, consisting exactly of those axes. So the curve consisting exactly of those curves, those axes, which have the following property: xf plus xf prime equals 2a. Okay, so that is an ellipse. That is an ellipse. Right. So that's a nice approach to a rather well. If it's not complicated, it's not complicated. It's simple, but it's difficult to grasp because, you know, mainly it is because it's three-dimensional, and so that's one thing. Yeah. So there remains the following question. So I have drawn up this. I have given you this illustration in the case where the plane intersects the cone in such a way that these tangents, these spheres of tangency, are on the same side of the apex. It can happen otherwise. I shall, however, leave the rest of the derivation to you because it's a very good exercise in three-dimensional arguments. You can have something like this. So let me take a cone which is a little fatter, like this, okay? And you may have a plane that intersects it like this, okay? So that the circles which are tangent to these three straight lines can be depicted as follows, okay, like this, and well, that's a little bit more difficult, and like this, okay, so when you follow this procedure and forget the spheres first, forget the circles first, and the plane, you can imagine this as a lateral view of the situation. Let's now, okay, so that's the axis. Let's rotate the whole thing about the axis to obtain a picture like this. I'm not going to draw the whole thing, but essentially what you get is going to be, well, these two spheres. So these will be spheres. Okay, so the whole thing will be a cone, and there will be a plane which will touch. So I'm not going to draw the plane because it's difficult to observe. Yet, to show you the position of the plane, I will, just as in this case, I will indicate the curve, and that curve will also, just as in this case, give you a feeling for how the plane is situated with respect to the cone. Now, in this case, the curve looks rather like this. It's a curve in which falls into two pieces like this. Okay, and you can in fact go through the same analysis. Everything will fall into place. There will be only one difference. That difference will be, of course, since the spheres of tangency are on different sides of the apex, then okay, so if you do choose a point and if you look at the distances, okay, from the respective foci in this case, okay, so in this case there will be two foci here and here. Well, if you do that, everything will work just as in this case, except that this formula will contain not the addition but subtraction. So you will in fact subtract xf, the length xf, and xf prime, and it will be of course done two ways. So you will take the absolute value, and that will be equal to 2a. Okay. Now this curve is called not an ellipse but a hyperbola. So an ellipse, a hyperbola. Okay, so there it is. So we've got these two interesting curves characterized. So that's what happens. So that's what happens if you intersect a cone with a plane. So that's, however, that's just one way of looking at the thing. There will be several other ways. Of course, as well, this is really the beginning of a very interesting story. Of course, there is, yeah. Perhaps I should mention also one other exceptional situation. It can happen. It can, of course, happen that the plane intersects the cone so that the plane, in fact, is perpendicular to the axis of the cone. Well, in that case, of course, you've got, well, let's look at it sideways. What you have got is, you've got the two circles, so that this initial triangle is an equilateral triangle, so that what you get is a situation in which the points of tangency of the plane and the spheres, they all coincide. So you've got the exceptional situation where f and f prime, so the two foci coincide. This gives rise to our well-known circle. Okay, so the circle obtains like this. So this description, this characterization gives you the ellipse. This gives you the hyperbola, and as a special case, it mentions, of course, this round, very round ellipse in which the two foci coincide. That's your circle. That's very fine. And think a little bit about this. There is, I mean, as I say, you are familiar with conic sections to some extent. There is one very important and very critical conic section, the so-called parabola. Okay, and parabola is, of course, as you will remember, obtained when the plane is parallel to one of the generating lines. Well, that object, that curve, is unfortunately not under. I am not treating that. That will require a certain amount of modification, and I shall do that modification in my. Well, I've got still time for that, so. But let's do it like that. Pekka, okay, so that's as I say, the first characterization. I would like to mention yet another characterization. That is, however, a rather different story. So let's stop.